convolution in the time domain is equivalent to multiplication in the frequency domain. And this is one of the most important properties in signal processing and signals analysis. So let's try to understand some intuition as to why it's the case. Here we have an equation in the time domain for the convolution. And let's think about the classic example of a linear system where the input goes into the system, which convolves with the impulse response of the system to give the output. This is what happens in all linear systems. Let's think about a particular case of the input and a particular case of the impulse response, and we'll build up our intuition about this property from there. Let's think about the system which simply delays the input. So in the impulse response, that is represented by a delta function at a delay tau. And let's think about an input, which is a sinusoidal waveform. So we're going to look at the cos waveform. So it's cos 2 pi f bar t. I put f bar because it's at a particular frequency. We're going to call it f bar. And here I've plotted an example of that cos waveform. So when you convolve a signal with a delta function, then it shifts your signal to have the zero located at the position of the delta function. And for more information on this property, you can see the description below this video where there's plenty of other videos on the channel explaining convolution and explaining convolution with delta functions. So the output in this case is going to look like this. It's still a cos waveform at exactly the same frequency. It is just shifted in time by tau, and that results in a phase shift. Since we've just simply got a cos waveform, the result of shifting it is to add a phase shift, has a phase shift theta. So the only thing that's happened, and this is one of the most important things to be noticing here, is the only thing that's happened is a phase shift. There has not been any change to the frequency. That's really the key to understanding this property. Okay, so let's look at that in mathematics to really convince ourselves. So we can rewrite with some trigonometric expressions. You can write cos of 2 pi f bar t minus theta in the following way. And there's a cos waveform, 2 pi f bar t, times a cos of the theta, plus a sine waveform, times sine of theta. And it's importantly, these two terms here do not depend on time. So clearly the resultant is you get a component of a cos wave and a component of a sine wave. The frequency has not changed. Okay, so now let's think about what happens if we have another delay in our impulse response in addition to this one. So let's say another delay at a bigger delay of perhaps tau 2. Well, in this case, you're going to have exactly the same output, but now shifted also to tau 2 and added to this output here. So what happens then? Does that change the frequency of the overall waveform? Well, no. The addition of two different cos waves with two different phases is still a sinusoidal wave at the same frequency. So for example, here with theta 1 and here with theta 2, when we add them together, because it's a linear process in the convolution, we could write each one of these two in the form above, and then you can see that each of these terms again would simply be the only oscillating components are cos and sine waveforms at the frequency f bar. So we'll be able to write this when there's a second delay in terms of an amplitude now, times the cos of 2 pi f bar t, still at f bar, plus a phase, an overall phase. And now we can think to generalize this. So here we've got two impulses, but in fact, you can now apply the same reasoning to any different delays, any impulse response ht. We can think of it as sort of an infinitely closely spaced set of delta functions. And this is a common way of thinking about signals in signals and systems. So for example, we can think of it like that. All these impulses infinitely close together, just like the example up here where we had two. Now we've got an infinite number of them to create our continuous waveform. So this property held when there were two, it's going to hold when there's a continuous function here for the impulse response. So the main point is when you've got a sinusoidal input to any system, you will get a sinusoidal output at the same frequency. That's really a key to understanding this property here. So let's think about that now in terms of the frequency domain. So now we're going to look and plot some things on this frequency domain over here. So this gain here, we can think of that now as, we can see that it is really the effect of the magnitude of the channel operating at that frequency. So here we've written little h here as a function of time, but when we look in the frequency domain, we're going to just simply use capital H for that. But the point here is the overall effect of the channel on a signal at the frequency f bar is to make its amplitude be scaled by A. So therefore we can write this as h f bar. This is the effect of the channel at the frequency f bar. The magnitude of that scales the signal, and the phase of it is rotated. So this is the phase of the channel at that frequency. So what does that look like on plots up here? Well, if we're going to plot magnitude here for the input and the magnitude for the output at the particular frequency here, f bar, then in the input, we have if we generalize this from simply a cos wave here with a unit input amplitude, let's now write the magnitude. We could generalize it to any amplitude at that frequency. So not just a unit here, but we're going to allow it to be any magnitude. So xf, any general one. And if we plot the magnitude, it only exists at that frequency, f bar. That's because it's a cos waveform. So it only exists at that one frequency. And on the input will be a delta function at f bar. The output will be at exactly the same frequency as we've shown here. The output now will be also a delta function, but its amplitude will be scaled. So now we'll have h f bar multiplying x f bar. And then if we're plotting the magnitude of it here, we'll have the magnitude. We can see that. So it goes in over here. I showed an example where it was a unit amplitude and it came out scaled to be h f bar as the output. Now, if we allow at that frequency any amplitude, x f bar, at that frequency, then the output will be the scaled version of x f bar. This is all at that one frequency, f bar. Of course, if we can do it for f bar, we can do it for all the other frequencies. The same property holds. Any sinusoidal signal going in at any frequency will come out at the same frequency, simply with its amplitude scaled and its phase rotated. So this property here doesn't just hold at that one frequency. Any function, any input function here, now we generalize from a sinusoid to any input function, but as we know, any input function can be made up of and written down according to the Fourier transform, and the Fourier properties can be made up of sinusoids. So any input system at all the different frequencies, they will simply scale at each frequency, will have this effect for that particular frequency. So if a signal goes in at this frequency, it will come out scaled at the same frequency with the scaling given by the channel at that frequency. So now hopefully you can see that leads us to the overall equation where the output in the frequency domain for any general frequency equals the input multiplied by the channel gain at that frequency. And therefore we've shown here that convolution in the time domain is the same as multiplication in the frequency domain. So hopefully this has given you more insights into the Fourier transform and into this vital property of the Fourier transform. And if it has, please give the video a thumbs up. It helps others to find the video. Of course, subscribe to the channel for more videos. And you can check out the description below. You'll find a web page that has a complete categorized listing of all the videos on the channel.